All right, so we're moving on to chapter 20 today. We're going to start something new called hypothesis testing. Let me write that down. So we need a new example to work with. A 1996 report from the U.S. Consumer Safety Commission claims that at least 90% of all American homes have at least one smoke detector. All right, this is going to be really important. We're starting out with the information that 90% of homes in the United States have a smoke detector. A city's fire department has been running a public safety campaign about smoke detectors, consisting of posters, billboards, and ads on radio and TV and in the newspaper. All right, so we're trying to get people informed, so they're doing this campaign where they're getting the word out that everybody should have a smoke detector. The city wonders if this concerted effort has raised, it's going to be important, raised the local level above the 90% national rate. So that's really the question. Did it work? We spent all this time, all this money to try to get people to buy smoke detectors. Did it work? Do we have more, right, raised above? Do we have more people than 90% with a smoke detector in their home? So to find out, right, that we want to know if this works, building inspectors visit 400 randomly selected homes. Right, notice that's probably not the entire city, right? We're just doing 400. That's very typical. We don't have the time or the money to check every home in the city, so we're doing a sample. We find that 376 have smoke detectors. So by the way, how did we do? Well, I'm going to call this P hat because this is the proportion of homes with smoke detectors based on my sample. We got 376 out of 400. And if I put that in the calculator, I get 0.94. That's 94%. So someone who is not taking statistics would probably say, hurrah, right? We wanted it to be above 90%. We got 94%. That's definitely higher victory, right? We were successful in our campaign. But we need to be more cautious. So the question is this evidence, strong evidence, that the local rate is higher than the national rate? Now again, if you just put this in front of just any person, they'd be like, of course it's gone up, right? 94% is certainly higher than 90%. But we need to be smarter than that. We remember that this 94% came from a sample. So it's not going to be exactly correct. This does not mean that 94% of homes in the entire city have smoke detectors. It's a sample. Samples have variation in them. So what I'm really wondering is did the campaign even work? Maybe, just go with me here, maybe there's 90% of homes with smoke detectors and we just got lucky. We just got lucky and happened to get 94% of homes in our sample with smoke detectors. So what I'm really trying to find out is, did this happen by chance? And that I can find out by doing what's called a hypothesis test. All right, so we're going to start out doing what's called a one proportion z-test. One proportion because I'm studying one proportion. In this particular story, I'm looking at the proportion of homes with smoke detectors. And we call it a z-test because we're going to use the normal model. So the first thing we need to do is write hypotheses. I know you're thinking I spelled this wrong because we're used to it being an I. Hypotheses is plural because we write two different hypotheses. The first one, this is H with a little subscript O. Subscript just means it's a little smaller. That is the null hypothesis. Okay, that's what it's called, null hypothesis. That means this is the hypothesis where we say nothing has changed. There's no difference. The word null means zero, so that's where I get that null difference. Excuse me, no difference. I also like to call it status quo. I don't know, that resonates with some people. So in my hypothesis, I'm going to be saying something about P, not P hat. I know what P hat is. I want to say something about P, right? The true proportion of homes with smoke detectors. Wow, I can't spell smoke detectors. All right, so I'm going to status quo, if nothing has changed, if the ad campaign did nothing, then I think, right, hypothesis, I think that my true proportion will be that 90%. And you'll notice I just like to write mine as decimals. It's just a preference. So the other hypothesis is going to be kind of our other situation. That A stands for alternative, so this is the alternative hypothesis. And this is usually what we're trying to prove. So we're trying to prove that the true proportion of homes with smoke detectors has gone up from that 90%. Now, I know you're going to be real tempted to say, well, we want it to be 94%. No, this is a sample. I really doubt that the true proportion is 94%. But what I do care to prove is that we went up from the national rate. So that's what I have listed here, right? P is bigger than 90%. All right, now we're going to take these hypotheses and we're going to investigate a little bit. I'm going to start by focusing in on the null hypothesis. Okay, I'll just leave that alternative for a little while. Forget about it. Right now we're going to focus in on the null, if nothing changed. So if the true proportion of homes with smoke detectors is really 90%, then the sampling distribution is going to look like a normal model. Okay, sampling distribution in your brain, you're thinking back to chapter 18. Oh yeah, the picture or the distribution of what possible samples could look like. It's going to follow a normal model, and it's going to be centered at P, right? And for the purpose of a hypothesis test, we're pretending, right, if, just making a little assumption here, that the proportion is that 90%. So this is going to be centered at 0.9, or 0.90. And it's going to have a standard deviation of 0.9 times 0.1 over the sample size of 400. And I went ahead and put that in my calculator, and I got 0.015. Okay, so that's what my sampling distribution should look like. So let's go ahead and take a look at a picture of that. I have to move my screen just a little bit. All right, so you'll notice I centered here at that 0.9. Again, we're with null hypothesis. If nothing changed, I should have my sampling distribution centered at 0.9. Then you'll notice I only went up and down 2 standard deviations. That's because, remember, outside 2 standard deviations is considered unusual. So that's why I did that. But remember also, for our p hat, this is what we actually saw. We saw a 0.94. Whoa, 0.94, that's like, I don't know, that's like out here. Certainly that's in the unusual territory. So it's unusual for me to see that 0.94. So let's kind of run through this one more time. If our city hasn't changed, right? Our city has 90% smoke detectors. It would be weird to sample and see 94%. So what does that mean for us? Well, we saw a sample of 94%. If the proportion is really 0.9, then seeing 94% is weird, right? I just said that. It shouldn't have happened by chance. It shouldn't have happened by chance. The problem is it did happen, right? This is, I mean, this is data. This is fact. We can't argue with it. It really happened. We saw it. So that means there must be something wrong in our thinking process. Our hypothesis must be wrong. If seeing this is weird, then this is not a good place for us to put the center of our sampling distribution. Okay, so in other words, right, we were pretending that this thing was true. Right? That's why I put it as the center of the sampling distribution. And we kind of explored some facts, and we ended up with some really bogus information. The 94% data shouldn't have happened. So that tells me that this original assumption was a bad one. So this is not a good idea. I'm going to reject it. Well, if that's rejected, then this thing must be true. The top one didn't make sense, so the bottom one must be the truth. Well, I shouldn't say must. Oh, excuse me, I wrote done. Must be true. All right, but I'm going to put a little caveat, right? Like probably, most likely true. All right, so it looks like we provided some evidence here. I am pretty darn sure that in this city, the proportion of homes with smoke detectors actually went up. All right, so let's put some numbers behind this. I said that seeing 0.94 was unlikely, but I want like a numerical value. How unlikely? What's the chance that we would see that? So in order to find out, here's 0.94, I'm going to ask myself, well, what's the chance I would see 0.94 or even something weirder, right? I mean, if 0.94 is weird, then anything higher would be even weirder. So I'm going to go ahead and calculate that, right? I can do that. I can figure out this shaded portion by calculating the z-score. Right? I observed 0.94. I'm going to subtract the 0.9 of the center. And just to remind you, the standard deviation was 0.015. So that gives me a z-score of 2.67. Okay, right? That's definitely unusual. It's above 2. So I can go ahead and calculate the probability of seeing that. Okay. So this, I'm going to need to check out my calculator. All right, so just to refresh your memory, we go to distributions. We're checking out the normal model. I'll zoom that in just a little bit more so you can really focus in on the screen. And I had 2.67, and I was going up forever, so that's comma 99. Wow. 0.003, let's round that to 0.0038. That is a pretty small chance, pretty small probability. So I'll go ahead and record that. This is a probability. We call it a p-value because hypothesis testing is so important and we do so much with it that this particular probability has a special name. It's called a p-value. And that is a pretty small chance. So if 90% of homes have smoke detectors, the chance of us seeing that 94%, tiny, right? Shouldn't have happened. Tiny probability. So I'm going to say something like this at the end. Since our p-value of 0.0038 is so small, right? Small chance, small probability. We're going to reject the null hypothesis. We throw it out the window. It's ridiculous. That means there is evidence that the proportion of homes with smoke detectors is above 90%. Okay. So notice this thing right here that I said, the proportion of homes with smoke detectors is above 90%. That's the alternative. There's evidence that the alternative hypothesis is true.